Hi guys, welcome to my CAPE Unit 2 Module 3 lecture on radioactivity. And before we get into the radioactivity concept at the CAPE level, let us revise a little bit on what radioactivity is. Radioactivity is a spontaneous random process in which an unstable nucleus tries to achieve stability, and it does so by nuclear disintegration. Now, radioactivity, if you consider it, why does a nucleus become unstable? And that happens when the nuclear forces are not strong enough to hold the particles at rest. Now, within the nucleus itself, based on the Rutherford model, you will see that you have protons which are positively charged and you have neutrons present. Now, the protons will have a positive charge, and as they are grouped together, they will tend to be self-repellent. So therefore, your nuclear force has to be strong enough to overcome those repulsive forces. Now, when we talk about radioactivity, synonymous with it is Einstein's equation. And we are talking about the energy released in a nuclear reaction being calculated by delta mc squared. Now, this equation came from the concept that Einstein said a change in mass is what is released as energy. Now, the delta M represents the mass defect or mass deficit, and it's the difference in the mass between the nucleus and the nucleons. Now, at the CAPE level, particularly with your multiple choice questions, you will always be asked if the mass of the nucleus is greater or less, and it's actually less than the mass of the nucleons. Now, when you use C of course is the speed of light, and you can use delta M in kilograms. If it is given to you in terms of U, common U, which is the unified atomic mass, then you have to convert it. I must also mention that 1 U is 1.66 by 10 to the minus 27 kilograms, but also 1 U is 9 to the 1.5 mega electron volt. So the electron volt is another unit for energy. Now, when we talk about at the CAPE level radioactivity, there is a new term called the binding energy which comes up. So in linking with what I previously said, that your nucleus has a lot of protons which are self-repulsive, and of course the nuclear force has to be strong enough to overcome that repulsive force. If we fast forward now to having a stable nucleus and breaking it up, then you need to supply energy. Why? Because work has to be done against the nuclear forces, right, which were in the first place present to kind of overcome the self-repulsive nature of a proton, right? So what you will find now is that the binding energy is the minimum energy which is used to do work against the forces. The binding energy is the minimal energy needed to separate the nucleus. That is, it has to do work to overcome the nuclear force holding them. So to separate the nucleus into the constituent nucleons, binding energy is used. Now, by definition, because you may be asked to define it in the exam, it is the minimum energy needed to separate a nucleus into its constituent protons and neutrons. Now, binding energy can be related to the stability of a nucleus, where the more stable a nucleus is, the greater the binding energy needed. Now, typically, you would have a curve here of binding energy per nucleon versus nucleon number. And as you can see, for very light nuclei, like from hydrogen to perhaps iron, your binding energy increases, which means that these smaller nuclei tend to be pretty stable, which is why they are typically used in fusion reactions. Now, when you have a larger nuclear number, such as uranium, you notice that there is a decrease in the binding energy. Having a lower binding energy means that you have less work that needs to be done in order to overcome the forces, which means that it is easier to have nuclear decay. It's easier to break up the nucleus. So those elements tend to be unstable. Okay? So the new thing in the 2018 syllabus is something called the island of stability. And this indicates that there is a certain proton to neutron ratio which would indicate a heavy yet a stable nucleus. And ideally, it was 114 protons to 184 neutrons. Now, within this proton to neutron ratio and neighboring values, they are tending to produce stable nuclei. But these values exist amongst heavy nuclei which are unstable. So because it's just a few elements with a certain range of proton to neutron values, we call them an island. And that is why it is termed an island of stability within a sea of instability. All right, so let us look at this equation.
What's not? Mommy.
Right, so let's look now at some equations, and I kind of summarize all of the equations that you would need for module 3. So one of the first things that we're going to look at is n is n0 e to the minus lambda t. Now, even though radioactivity is a random spontaneous process, it can be statistically modeled using an exponential decay. Now, at the Form 5 level, you would have visited the fact that half-life is the time taken for a sample to decay to half its previous mass, activity, or number of nuclei. In the same way, when we talk about a decay constant, right, that's a new term you will see at the CAPE level, that is looking at a ratio of the activity to the number of nuclei. Now, in Form 5, you would have looked at activity in terms of number of disintegrations, right? But in Form 6, we call that activity, and it is represented by the unit Becquerel, BQ, right? Because Henry Becquerel, he worked with radioactivity. Now, activity is equal to minus lambda n. So that's one of the equations you need to learn. So we don't have to use a negative sign because the negative sign just indicates as radioactivity decay occurs, n, which is the number of nuclei, would decrease, right? So it's indicating that n decreases. So you'll use the modulus of the equation, okay? You also could find the decay constant because it's a ratio. If you ask to define it, it's a ratio of the activity to the number of nuclei. That is equal to ln 2 over the half-life, okay? Now, here, you will see that we can model radioactive decay as well with this equation. So here, I could have actually said A is A0 e to the minus lambda t. So t will tell you in a certain time what would be the activity. And of course, you would need to know the initial one, okay? All right, so let's look now at this, just two examples. The first one is how many atoms exist in 2 grams of radon, and it has a mass number of 226 and atomic number of 88. So just like your chemistry calculations, to get the number of atoms is the number of moles by Avogadro's constant. So to determine the number of moles, it is mass over molar mass. So that's 2 over 226 by Avogadro's constant. So when I worked it down, I got 5.32 by 10 to the 21 atoms. If you were told, right, the same question, what would be the half-life of the sample? If the half-life was 50 years, what would be the decay constant? So, you know, you have to kind of look and play up with what you are given, right? I teach my students that. You apple pick. That's my term. So you pull out the pieces of information and then you try to create a bridge or a link between what you know, the equations, and how to solve the question. No question is unsolvable. You have to learn to think. Right? You have to develop your skills, and that only comes with practice. But you cannot practice what you do not know. So you have to be very coherent with your theory. So ln 2 over the decay constant is your half-life. Now, even though your decay constant is like basically a time value, that is per second, per year, right, per hour, you just have to make sure it's coherent with what is given in the question. All right, let's look at this example now. So let's say you have a sample of carbon-14 and it has an initial mass of 1 by 10 to the minus 6 grams. So you have a little table and you were told of activity versus time. So of course, you know, you get typical exponential graph. Now here, you were asked firstly to determine the initial number of atoms. And remember guys, when you have the initial number of atoms, this value would be A0. And that is coherent with your use of the exponential equation. So here, to get the number of atoms, you get the mass over the molar mass multiplied by Avogadro's number, right? And then you work it down to get A0. If you were told to get the decay constant, as I mentioned previously, it is always a modulus, right? Because you don't have to include the negative sign. That's just showing a decay. So it is A, the value, over N0. Right? And that is why A0 is important. A0 is your initial activity, and if you go back to the table, it is the first value here, your initial activity before any decay has happened. All right? And of course, because my times were given in hours, the value would be per hour. So to get the half-life, it is ln 2 over lambda, and you work it down. Right? To get the activity after 8 hours, we're just going to use the equation A is A0 e to the minus lambda t. So we have t being 8 hours, and you substitute it and you work it out. So this is a typical example of a question. If you go to my book, Cape Revision Guide Unit 2 Physics, available at any Muhammad's bookstore, you will see more worked examples. And again, when you go through the worked examples, they mirror the past paper questions. So once you understand how to do the worked examples, you'll be fine with the past papers.